Let's look at the case of interprocess communication. Right? So I want to communicate between two processes. So app 1 is going to, let's say, do a write. Okay? So this happens first. If we look at the code in app 1, it's going to write and then read from app 2. That is, read the response. App 2 is going to read from app 1 and then write to app 2. Let's just give an example. Let's say app 2 is, I don't know, it is a pi server. So we write and we ask it, what is the nth digit of pi? And it writes back the nth digit of pi. Okay, it has a big table or it has some fancy mechanism for calculating this, who knows what, but that's what that does. So we ask for a digit of pi and it gives it back that digit of pi. Okay, it's like a remote procedure call. So we're talking here about interprocess communication. And what this actually might be is a socket that we've set up. So we've set up a socket that's such that we can read and write. So if we looked at this, this might be a socket gives the abstraction of a read and writable pipe, let's say, okay, where write on one end appears as a read on the other, and vice versa. So let's look at what actually happens here. We're going to have a write by app 1. So that's going to be a write. That's going to go into the kernel. The kernel, and so we have crossed our user kernel boundary once, going on this write system call. Now, once we do the write, this is blocked, let's say, until this write completes. And now we, application 2, so this is app 1, this is app 2. Application 2 has done a read somewhere or other here. I don't know, let's say here. I can't run at the same time, so let's say it's here. Okay, it does a read. What happens on the read? Well, if the write hasn't happened yet, it blocks. If the write has already happened, then the read we can continue. Let's say it does block. So let's say app 1 actually does its write here. So we go to the kernel for a little bit of time, and app 1 does its write. So at this point, we go back in the kernel, and then we can wake up app 2. App 2 runs. It now calculates whatever pi is by whatever mechanism it has and does a write. So it does a write. We're back in the kernel. We go back up on here, and then we start running, and we do a read. So we switched from user to kernel once, from kernel to user twice, 3 times, 4 times, 5 times, 6 times. When we do the read, we come back into the kernel 7, 8 times. So 8 times we're crossing back and forth between user mode and kernel mode. And we have a lot of context switches, right? Each time we're switching from app 2 to app 1, back to app 2, back to app 1, that's all a context switch that requires a TLB flush. Let's look at the way it's done on Aegis, okay? So the system calls. One is yield, can actually take an argument, which is a process to run. So I am not just arbitrarily saying, I give up time and run whoever you feel like running. It's, I'm giving up time, but I want it to go to this other process. So on this, what happens is the kernel upcalls. The kernel leaves the registers alone. That is, they maintain their value from app 1 into whatever this other process is. So those registers can actually be the information that is being transferred across in the IPC. So this is app 1, let's say. Now we're running in app 2, and app 2 gets all the registers from app 1. All right? So what did it have to do to make this IPC? It could just, let's say, push into EA, well, assuming that we know there's a MIP CPU. So put into a specified register, let's say the digit we're interested in. Make this up call into the process. The kernel knows how to go into a specific up call. So what up call is this? I'm not sure. You know, it might be IPC enter. Who knows? So it gets all the registers from app1 and app1's identity. That is, it gets told who sent this to you. And then it can just do a yield to app1. Again, those registers maintained. So if we look at the calls that happen, basically we have app1 is running, does a yield to app2. The kernel does a little bit of work, and then app2 runs. This is at the up call. App2 does a yield back to app1. And now we're in our up call, and we have all the registers from app2. So app1 said, I'm in a register, I'm going to put the digit of pi I'm interested in, and app2 then says, well, I'll return you in that same register the value at that digit. So if we look at the number of crossings, we have 1, 2, 3, 4. We only have 2 context switches that require flushing the TLB. So this is about as quick as you can imagine it, in the sense that I am making a system call. It is going to a specified location in this application, and then the application is making a system call to go back. And we also know that it directly, we're not waiting for application 2 to be scheduled again. We don't have to send an IPC and then wait for app2 to become the running environment. We might have a lot of different environments running, and it's last on the list. This allows us to just quickly say, use my quantum of app1, but go ahead and run app2 for just a little bit.